Welcome. Let's take an excursion into the fascinating world of prime numbers. We will explore Euclid's brilliant insight, a simple yet powerful idea that guarantees prime numbers never end. Let's embark on this journey to understand the infinite nature of these fundamental mathematical building blocks. Prime numbers are the building blocks of all whole numbers. A prime number is a whole number greater than 1 that cannot be formed by multiplying two smaller whole numbers. The smallest prime is 2. By the way, conventionally, we do not consider 1 a prime. Numbers that can be broken down into the product of other whole numbers are called composite numbers. Do prime numbers eventually run out as they get larger and larger? That is a great question, but we cannot simply look at a long list to decide. Instead, we need a logical approach that works for any finite list of primes, proving that we can always find another one. To prove this, we use the logic of contradiction. We start by assuming that the list of primes is complete and finite. Then, we construct a special number using this list of prime numbers. If we find a prime factor not in our original list, our assumption fails, proving the list was incomplete. The engine of this proof is simple. Multiply all the primes on your list together, then add 1 to the result. This gives us a new number, and we call it n. This construction is key to showing that our original list could not have been exhaustive. The beauty of adding 1 is that it creates a remainder. When you divide our new number n by any prime from your original list, you will always be left with a remainder of 1. This guarantees that none of those primes can evenly divide n. Let's test this with the list 2, 3, and 5. Multiplying them and adding 1 gives us a new number, 31. Notice how dividing 31 by any of our starting primes always leaves a remainder of 1. In this case, 31 itself is a prime, not on our original list. It is a common mistake to assume this process always produces a prime number. Sometimes, the resulting number is composite. However, even when composite, its prime factors will not be found on your original list, still proving the list was incomplete. Whether the new number is prime or composite, the conclusion remains the same. There is always a prime factor that was missing from your initial list. This confirms that no finite list can ever contain all prime numbers. Prime numbers exhibit a unique beauty. While they become less frequent as we look at larger numbers, they never disappear completely. There is an underlying order hidden within their seemingly random distribution. Infinite does not mean evenly spaced. Some primes appear in pairs, known as twin primes, such as 3 and 5, and 29 and 31. There can also be vast, prime-free gaps. The existence of these patterns and irregularities remains a significant area of mathematical study. Our modern digital security, such as RSA, relies on these properties. By multiplying two massive primes, we create a number that is easy to compute but extremely difficult to factor. It is the infinite and unpredictable nature of primes that keeps our data secure. As technology evolves and quantum computing threats emerge, our security standards are also shifting. Yet, prime numbers remain the bedrock of modern mathematics, continuing to support algorithms and coding theory in this new digital era. In summary, every attempt to find a final prime only creates a new beginning. Euclid's proof elegantly demonstrates why the search for prime numbers can never end. Infinity is not just a concept here. It is mathematically guaranteed. Thank you for stopping by. Enjoy some good mathematics at your prime time every day.